This is section, what is 12.1, talking about parabolas. The work we've done so far has been strictly with the algebraic definition of parabolas. And that definition is y equals a squared plus bx plus c. Okay? Knowing that if a is positive or concave up, a is negative, concave down, we've done the vertex form and completing the square process to change that to graph it using those techniques. Today we're going to talk about how we can graph a parabola using the geometric definition. Okay? Before we get into the geometric definition, I always want to talk about collectively what conic sections are. Conic sections are this process here, or this understanding. We take two cones, two congruent cones. They have the same radius. They have the same height. The process then is to put them so that they are mirror images of one another against their vertices. Okay. Something that I think is also important to talk about is the altitude of these things, and I've got a picture over here of this. Okay, so the altitude of a cone is from the vertex perpendicular to the circular base. And then this distance here, we call that the slant height. Those are things that we learned back in geometry. So I might use those words here in a moment. But what we do for conic sections, the way we develop these parabolas, for instance, is we take a plane and we orientate that plane with some degree, or we consider it a slope essentially, and it intersects our cones. That intersection is called a cross-section. We take a plane intersecting a three-dimensional shape, you get what we call a cross-section. And that cross-section for us right now, the way this plane is oriented with our cones, is that blue curve. And that blue curve is our parabola. Okay? The idea is when we take our B equals A, so we take these angles. The angle A is ultimately telling me it's half of that basically that vertex angle of our cone, and B is then the slant or the slope of the plane. Okay, so if those two angle measurements are the same, then basically saying that the plane is parallel to the slant height of our cone, and we're always going to get a parabola. Okay. If I take my B value and make it 90, okay, so my plane is now parallel to the base of the cones, you see that cross section is a circle. Okay, and we can move that plane anywhere we want to, but we always see that we're getting a circle. If I do this, so now the angle of my plane is greater than the angle of that cone, that vertex angle of the cone, or half the vertex angle of that cone, we get an ellipse. Okay, so this obviously the cross section here, you're not seeing so much as an ellipse. I think it's kind of distorted a little bit. But if I look over here, that cross section is an ellipse, and if I make that even a greater difference in the degree, or I guess brings the degrees of these two things closer to one another, we do see that we're getting an elongated circle there, or an ellipse. If I go far enough with that thing, we end up getting that plane to intersect both of our cones, okay? And when we get that intersection of both cones, we get this cross-section, which is a hyperbola then. So those are our cross-sections. Obviously, then they're sections of cones, or we call them conic sections. Each one of these has a algebraic equation, okay? But we're going to arrive at those algebraic equations through the use of a geometric definition, okay? So that's kind of what we're going to try to investigate here with parabolas, ellipses, circles, and hyperbolas. First one obviously being a parabola. So this is what I want to talk about, the geometric definition. So the geometric definition of a parabola is a parabola is the set of all points. Something you might see as well, when they say set of points, set of all points, they might write locus of points. Okay? A parabola is the locus of points in a plane that are equidistant from a fixed point F, called the focus, and a fixed line L, called the directrix. Locus is just a math word for kind of a group or set of points. When we talk about this definition, see, I've got another GeoGebra here. I'm just going to open it. What the definition is talking about, that focus is always going to be on the interior of your parabola. The directrix is some horizontal or, some cases, vertical line that we're going to use. So right now, I've got my directrix being this black line right here. I'm going to take, let's see here, this point A. I'm just going to put it so it's, and I'm going to actually move my focus too so I can do this a little bit easier. If I do that, right now, the focus and this point A on my directrix, they are vertically aligned with each other. Halfway in between, so this point 2.25 and this 2.25, those are the distances from the focus to the parabola and then the parabola to the directrix. The definition says as long as those are equal, that point C should be on my parabola. And in this case, that point is going to be my vertex. As I move this point A, that 2.25 is going to grow. Okay? But you notice that the distance between the parabola, okay, and the directrix, that distance there, is still the same as that distance there. And that's what the geometric definitions of a parabola says should be true. Okay, so out there I get those two distances to be the same. So I've got now the kind of the right-hand branch of that parabola. If I go this direction, we get the same thing. Okay, so as long as I maintain that distance to be the same as that distance, the point there is going to be on my parabola. Okay, so that's what we're looking for as the definition, the geometric definition of a parabola. All right, so that's what this picture is dealing with. There is, with every parabola, we talked about this with our algebraic investigation. There's an axis of symmetry here. That axis of symmetry goes through the focus. It goes through the vertex, okay? And it's going to be perpendicular to your directrix. All of these distances here, all these yellow vertical distances, they are perpendicular to the directrix as well. All of these are right angles. And if you remember why, we go back to geometry. If we have a point not on a given line, so point P here is not on my directrix, the shortest distance to that line from point P is through the use of a perpendicular line. Okay, so that's what we're looking for. And then obviously there to there, that distance has to be a straight line. Okay, we'll talk about how we find that distance here in a little bit. All right, so how do we generate a formula off this geometric definition? So this is a little bit of what we call analytical geometry. We've done a little bit of this with you guys back in geometry. We've done a little bit in algebra so far. But this is, I think it's a very important practice for us to be able to do. So deriving the equation of a parabola, it says we want to come up with the formula for a parabola. Well, we're going to use that definition we just talked about, and the fact that in any parabola, if I have a point on my parabola, if I have this point P on my parabola, okay, then the distance from point P to my focus should be the same as the distance point P to my directrix. So those yellow distances need to be the same. All right. Now, when we try to figure this out, the best thing to do to make our algebra a little bit easier and to make it a little bit more simplistic, I guess, is that we place this parabola in a convenient spot. We place its vertex at 0, 0. Okay? And the idea of that is, why can I do that? It's ultimately, when I have a parabola just kind of floating around in two-dimensional space, and I have my x and y plane, okay, I should be able to take that x and y plane and always move it as kind of like a transparency to where it's on the origin is on the vertex of that parabola, no matter where my parabola is. Okay, and I can do it vice versa. I can take the parabola and I can always shift it to where its vertex is on 0, 0. So that's what we're doing right here in this. We want this red parabola to have a vertex of 0, 0. Our focus is always going to be on the axis of symmetry. So right now, by placing that vertex on 0, 0, we know then our axis of symmetry is the y-axis. Our focus then has to be on that. Our focus can be anywhere. And we'll kind of investigate this here in a little bit. Actually, maybe do it right now. The placement of my focus is going to kind of change the width or the vertical stretch of my parabola. That's the only thing it does, okay? So as I move this focus up and down, this parabola might get flatter or it might get taller, but that p-value is going to be some number on the y-axis. That means then that this distance from the vertex to my focus is p units, okay? Now, when that point right there on my vertex, so we said by definition that point has to be equidistant from the focus and the directrix. So that allows us to say that distance there has to be p as well, okay? Because every point on here is going to be equidistant from the focus and the directrix. So eventually when that point starts to slide down and become there, the distance from the focus to that point is that, and the distance then from the point on my parabola to the directrix is that, and those should be equal. So if one's p, the other one's p. And that's nice because now if that's p, that distance is p, and the directrix is a horizontal line, well then y has to equal negative p for the equation of that line. So that's kind of how we set everything up here. And now we're going to go abide by the definition to see if we can come up with an equation. The definition says that distance has to be the same as that distance. Well, distance in the coordinate plane, back to geometry, is the change in x squared plus the change in y squared, and then you take the square root of that. Well, if I take the distance of f to p, subtract those x's, so subtract that one and that one, I'm going to do it x minus 0, so x minus 0 is just x, and then I square that. I'm then going to do the same thing for the y's, that y and that y. So add to it the difference in those, y minus p, and I square it. Doesn't matter the order that I do that, I just go y minus p in this case. All right, so we now have that distance. Well, that distance needs to be the same as this distance. This distance here from my point P to my directrix, and I'll just put capital D here for directrix, that distance, a little bit easier to find because it's a vertical distance here. If my directrix is horizontal, my distance here has got to be vertical. It's got to be perpendicular. So if this point here is at x comma y, that means to go from 0, 0 to it, I had to go over x and then up y. So that distance right there is y. Okay. Well, this distance here, that is the distance from the horizontal line that holds my vertex and my directrix. We talked about that distance had to be p. So now if I want to find the distance from that point down to my directrix, all the way down, it's y plus p. Okay, now we sometimes put, or we should put absolute value bars there because we want distance to be positive. And we're going to talk about how maybe that kind of disappears here in a moment. So these two distances have to be the same. So that means that these expressions that gain those distances, x squared plus then y minus p squared, needs to be equal to the absolute value of y plus p. Now, I'm going to solve for x squared. Okay, and I'm going to see why here in a moment. When I solve for x squared, the way I'm going to do that is I got to square both sides. So I'll square this side, and then I'll square this side. Okay, but when I square y plus p, okay, regardless of what y plus p is, positive or negative, when I square it, it's going to be positive. So what we're saying here is these absolute value bars kind of just drop out. We don't deal with them anymore for the mere fact that the squaring is redundant in regards to what the absolute value bars do. Okay, so we don't need them. A lot of times in textbooks, they'll just drop them out, and you're not really sure where they went. It's because when I square, that's going to be positive anyway, so it doesn't really, the absolute value bars really don't matter. On this side over here, we'd be left with x squared plus y minus p, that quantity squared. Okay. I'm going to just solve for x squared here. So it becomes x squared is equal to y plus p squared minus y minus p squared. All right, so that's ugly. We should be able to clean this up a little bit. And I'm running out of room, so I'm going to move this down a little bit. And it's kind of backwards, but I'll take this work over here. If I expand those things, expand the right-hand side, I have x squared on the left. We have y squared plus 2py plus p squared. Okay, and then we would have, if I expand this thing, now I've got a minus out front, so it's got to be minus whatever that trinomial turns into. So it'd be minus y squared. When I multiply these, it'd be negative 2py, so minus negative 2py becomes positive 2py. And then I'll square negative p, so it gives me p squared, but it's going to be minus p squared. Okay, so this thing here expands to this. Well, when we do that, there's some nice things happening here. Y squared, negative y squared. P squared, negative p squared. 2py gives me 4py. In this case, x is our x variable, y is our y variable, like any other problem that we've dealt with. But the 4p, that 4p is going to dictate then kind of the behavior of that parabola. Where p is the distance from your vertex to your focus, or from your vertex to your directrix. Okay, and we'll talk about something else that 4p represents here in a little bit. This here, then, this breakdown kind of explains all the things that exist for this type of parabola. A parabola opens up or down, x squared equals 4py. That's the geometric definition of a parabola. The vertex is always located at 0, 0 with these. I'll talk about how we can change that later on. The focus is always at 0, p, and your directrix is always at the opposite of that p. Okay, if p is positive, your parabola is going to open upward. If p is negative, your parabola is going to open downward. Okay, I suggest you see me say this here, and you're going to see this in all these videos that I do with conic sections. Fight the urge to try to memorize all that stuff. Develop relationships. Okay, understand that the focus is going to be the same distance from the vertex as the directrix is. So the vertex is halfway in between the focus and the directrix. That's going to be huge for you. If my p-value is positive, or I guess not necessarily positive, but if I know my location of my vertex, or not my focus, sorry. If I know the location of my focus is always on the interior of my parabola, okay? So if my focus is 0, -2, okay, then my parabola's got to open downward so that the focus is on the interior. So those are the kind of things that I remember that I think help a little bit more than trying to memorize this stuff. So we get to some questions here, some specific examples of how we can develop these equations. It says find an equation for the parabola with vertex at 0, 0 and focus at 0, 2 and sketch its graph. Well, if its focus is at 0, 2, okay, its focus is at 0, 2, so my focus might be right there. Okay, my vertex is right there at 0, 0. Okay, my parabola has to be containing my focus. So my focus has to be on the inside of my parabola. So my parabola is going to open that way. I know that this distance here is p. So if I repeat that distance down here, my directrix should be that line right there. My directrix is line y equals -2. So now if I want to find the equation for this. It's opening upward or downward. So it's going to be of the form x squared is equal to 4py. Well, remember, p was the distance from your vertex to your focus or from your vertex to your directrix. So that distance is 2, so you got x squared is equal to 4 times 2 times y. So x squared is equal to 8y. Okay, so that's pretty useful tool now to develop the other points that might be on that parabola. If I want to say, what happens when y is 2, okay, so when y is 2, so if you go 8 times 2, that should give me x squared, right? So then x squared is equal to 16. If I want to solve for x, it gives me plus or minus 4. So I have another point here. I have another point, or set at 2 points, I guess. X was positive 4. The y value I used was right there, which was 2. And then I'm getting negative 4, 2 as well. So negative 4, 2, maybe that point right there. Negative 4, 2. And then this point here would be 4, 2. Something I want to talk about later on in this PowerPoint is if I connect those 2 points, okay, with a horizontal line essentially that goes through the focus right there. That's the focus, remember. The distance of that red line is 8 units. The distance of that line is 8 units. That 8 units was what 4p was. Okay, so that's going to be something we come back to here in a little bit. But the equation, if that's all I'm asking for, x squared is equal to 8y. Sketching it, I think it is important maybe to find those extra points. That's not the only set of points you could have found. You could say, okay, what if I let y be 1? Then I have x squared is equal to 8 times 1. And then x would be plus or minus 2 root 2. So you'd have 2 root 2 comma 1 and negative 2 root 2 comma 1. And those points would also be on your curve. This one down here in the bottom says find the focus and directrix of the parabola y equals negative x squared and sketch the graph. Okay, so that one we now know the equation. The equation says y equals negative x squared. Now, if you think about what you've already done in the past, you know that that's located at 0, 0. We know x squared has the point 1, 1, negative 1, 1, 2, 4, negative 2, 4, but that negative flips them all. So we would have a parabola that has concave down. We know how to do that through what we've done in, basically this first semester of college algebra. If I want to use the geometric definition of this, because it does ask for the focus, the direction, and the location of that. If we remember, this does not locate, the algebra does not ever locate the directrix and the focus. So what we do is we try to take this and rewrite it so that it is in the x squared equals 4py format. And right now it's not. Right now, the x squared is negative. So if I do this, take this y equals negative x squared and rewrite it this way, x squared is equal to negative 1y. Now this thing is in this geometric format. And what we're seeing is that 4p is what's generating this negative 1. So we got a little equation here. It says 4p is equal to negative 1. P then obviously is negative 1/4. So when I want to find the parabola using this technique, and it asks me for the focus and the directrix, okay, because p is negative 1/4, and the focus is always at 0, comma p. My focus is going to be at 0, comma negative 1/4. So I find 0, negative 1/4, so maybe it's right there. That's my focus. My directrix is always opposite that. So I go, there's my vertex is going to be at 0, 0. My directrix then is that distance on the other side. So that distance is 1/4. So up here I have y equals 1/4 as that directrix, and then the parabola obviously has to open downward, so the focus is inside the parabola. And if we needed to, we could obviously then find some other points. We would see -1, -1, and 1, -1 are on that parabola and so forth. Just using GeoGebra a little bit, maybe, to see that that is indeed what we're looking at. We know that if I graph y equals -x squared, we get that, okay? But if I graph x squared equals -1y, we get the algebra up here, we can see that they produce the same curve when we toggle that back and forth on and off. If we put our focus in, so f equal to 0, -1/4, be that point there. Y equals 1/4, be that point there. So that information, that's my directrix and my focus. So the idea then is, does this mimic the definition of a parabola by the geometry? So what I'm going to do is I'm going to figure out what is the distance from F to A. That's 0.59. And now I got to find the distance from A to my directrix. That's a little bit harder with GeoGebra, but I got to go from, I find a line that is perpendicular from A to there. And now I just want to find A to B. So I'll ask you to do that, A to B, kind of hide everything else here. I don't need that entire line. So then I look at those two segments, G and I. So that's I, and that one's G. As I move A, you see that those distances are always the same. And right there you're seeing that's that 0.25, okay, and keep going. Okay, and we see that those distances are always the same. So it's kind of a neat way to deal with parabolas. The same thing can happen, okay, we can have parabolas that open to the right and to the left. Now these are not functions, okay, because they would not pass the vertical line test. But if I just interchange the x's and the y's, we get parabolas that open up to the right and open up to the left. In this case, we still have the same vertex at 0, 0, but now you see at the focus, the x's and y's kind of change. Now it's p, 0 instead of 0p. Now the directrix is a vertical line, so it's x equals the opposite of where p was. If p is positive, that's what we're seeing here. It's open to the right. If p is negative, it's going to open to the left. And so we'll see an example of that. Okay, so the parabola has an equation 6x plus y squared equals 0. If we're going to use what we've learned in algebra so far, maybe we'd do something like this, like y squared is equal to -6x, and then we'd go y is equal to plus or minus -6x. All right, and then we would go y equals positive root -6x, and y equals negative root -6x. Now, most of you are probably, or some of you might be thinking, well, you got a negative in there, I can't do that. Well, let's remember this quantity is only negative if I choose x to be positive. So x being positive, this thing does not exist when x is positive, because that would give me imaginary results. So x has to be negative. If I do x to be negative, this would give me the square root of, let's say x to -1, and give me the square root of 6. So, and I keep doing that, if I get square root of 6, give me a positive number. Square root, if I put x to be -2, I get a square root of 12. That's going to be a positive number. So this thing here would give me a curve that looks like that. Okay, the one on the bottom would give me a curve that looks like that. If I put them together, obviously you get that parabola. Just showing that, just so you're convinced with GeoGebra. If I go y equals the square root of -6x, you see that branch. If I go y equals the square root of, actually the opposite, the square root of -6x, you get that bottom branch, and then together those are the parabola. If we think about it, is it the parabola y squared plus 6x Yeah, it's going to be graphing, I think, in the 3-dimension. Yeah. But if I look at it that way, I know that's not, I don't want to explain why it's doing that. But if we look at that, basically when we talk about y squared plus 6x with GeoGebra, it's going to graph a, not a plane, but a surface. And that surface there is parabolic, but it is showing essentially the same thing that we're interested in here. Okay. Just the way GeoGebra graphs those implicit equations. All right, so how do we do this using our geometric approach? Okay, well, if I rewrite this as y squared is equal to negative 6x, okay, well, we said y squared should equal 4px for any parabola that's opening left or right. Okay. Right now we're seeing that negative 6 is being generated by that 4p. So if I say negative 6 is equal to 4p, divide both sides by 4, I get negative 6 over 4 equals p. P then is negative 3/2. Okay. Now p equals negative 3/2, meaning I don't. And this is what I was talking about. If I go back to that blue slide or that blue graph, it told us if P is negative, this thing opens to the left. If it's positive, it opens to the right. I don't care about that. I know that P is the distance from the vertex to my focus. So if I go over negative 3/2, I know I'm going to have to go to the left. So negative 3/2 may be that point right there. Okay, so negative 3/2, comma 0, that's my focus. Okay, meaning then over here at negative 3/2, x equals negative 3/2, that is my directrix. My parabola has to open towards my focus. Okay, so there we're getting that same curve that we got by using maybe our algebraic approach instead. Some other points that would be on there, obviously, if I have y squared equals negative 6x, okay, choose an x value. Maybe I choose, x to be negative 3/2. So when I do that, I get 9, right? So I get y squared is equal to 9. So then y would equal plus or minus 3. So when x is negative 3/2, I can come up here and say at that point there is negative 3/2, comma 3. And this one down here is negative 3/2, comma negative 3. Again, look at this distance. If I look at that distance, as long as it goes through that focus, look at the distance of that. This one's 3. That one's 3. Okay, so that's a 6 total. And that 6 comes from that 4p. Okay, I know it's negative, but still it's a distance, so it's positive. So 4p, that distance there is always equivalent to that line right there. And we'll talk about that in a couple slides. We'll identify the name of that thing. Let's see here. Oh, it's right here. That distance. So whenever I have a point that is, so here's 0, 0. Okay, that's my vertex. Okay, if I travel to my focus, that's P0. So this distance over here is negative P. This point here, Q, every parabola is going to have this. There's going to be some point Q in which to get to Q, I'm going to have to go over P units and then up 2p units. Okay, and the idea there is that at some point, that distance right there, okay, that 2p distance has got to be equal to that 2p distance. Okay, that's the definition of a parabola, that the distance from the directrix to the point on the parabola is the same as from the point to the focus. So if that's p and that's p, that distance is 2p, this here has to be 2p. That means this here has to be 2p. So this yellow line that's going through here, okay, goes through point Q, starts at point Q, goes through our focus, and ends at this point. Let's just call that point V. That segment there is called the lattice rectum. And the lattice rectum, if that distance is 2p, that distance is going to be 2p because the idea of symmetry for parabolas. So the lattice rectum has a length that is always equal to, so has length equal to 4p. Okay, now that length, the lattice rectum length, is usually called the focal diameter, meaning that it's the distance that it's the segment or the distance of the segment that passes through your focus with endpoints on your parabola. Those are 3 points that are pretty good to use. The vertex and then the endpoints of your lattice rectum are pretty good points to use to graph every parabola. The parabola, and a lot of our conic sections have these types of properties here. We call it the reflective property of a parabola. And this is mainly with sound and light. If you were to go to your car and look at your headlight of your car, okay, and look at the lens of that headlight, not the lens, but the concave reflective surface, it's going to be parabolic. It's going to be called parabolic bowl. And the reason for that is to address or to use the reflective property of a parabola, okay, to harness the physical property. And that physical property is the fact that if I have a light source at the focus, so the filament of my light bulb is at the focus, when that light turns on and those rays, those light waves emanate from that focus, they're eventually going to hit that reflective surface. That's why, that reflective surface is usually like a mirror type coating. It's going to reflect that light away from the focus and away from the parabola, but it does it no matter where those light waves go. That light is reflected in a parallel fashion. All these beams of light are then going to be parallel to one another. And the idea here is that there is a tangent line right here, and whenever you think about this in like a game of pool, if I hit a ball off the rail of a billiards table, the angle of incidence is equal to the angle of reflection. So the angle of incidence here with that tangent line is going to be equivalent to the angle of reflection for this light, okay, or essentially if we're thinking about it as that wave, okay. So it's all going to be focused then in the same direction, so now we can light up everything that's in front of us. The same thing happens when we talk about sound, and this I think is maybe a little bit easier for people to recognize or understand. Maybe you've seen this somewhere. If I go to, say, even if you watch like football on TV or something like that, you might see on the sideline somebody with a parabolic microphone. They are these things. Okay, so, and actually it's probably this one here that you see because it's usually a pretty big one and they've got it strapped to them. But that kind of acrylic shield thing is a parabolic bowl. And if I look at this one here a little bit better, that little black thing in the middle is located at the focus of the parabola that is defining that bowl. And what happens is that sound waves emanate from out here and they come in and they hit that bowl. And once they hit that parabolic bowl, they are redirected towards the focus. And what we have right here at the focus is a microphone, okay? And now we can hear that ambient noise a little bit better. And we can hear the activity on the football field or the soccer field or whatever. We get a more immersive experience while we're sitting at home watching TV. Because this allows us to harness those sound waves and interpret them and magnify them a little bit better. Same thing happens with like satellite dishes. So you got a satellite dish on your house or whatever, DirecTV, whatever it is. You know, even you see these types of satellites that we use a lot of times for larger communication than just like radio waves or TV waves. This little thing up here is located at the focus, is whatever this receiver is located at the focus of this parabolic lens. Okay? There's a giant, I forget what it's called, giant satellite, and I think it's Puerto Rico. Maybe not. Yeah. Okay. The Arecibo Observatory. Okay. Which we use to, you know, see into space. Okay. It's a very, very powerful telescope, essentially. But this surface here is parabolic, and you see this thing up here is a receiver that is located at the focus of that parabolic bowl, and all the light waves that, or whatever we're using this thing for, are bouncing off of this bowl and being reflected back up to then that receiver, and then that data is collected and we reinterpret it and all that kind of stuff. So there's a very, very real life good use for these parabolas. One last question is this, and this is kind of addressing that idea with the light on your car, or a searchlight in this case. So a searchlight has a parabolic reflector that forms a bowl, which is 12 inches wide from rim to rim and 8 inches deep, as shown in the figure. So the filament of the light bulb is looking at the focus. How far from the vertex of the reflector is it? So we basically want to know, if I'm going to install this light bulb, where do I have to put it inside this searchlight so that we optimize the reflective property of a parabola? Well, if we think about this parabolic bowl is going to have, if we were to take a cross section on it, it's a parabola. Okay. The idea is, if I take that blue curve and make it two-dimensional, okay, and you talk about this a little bit in calculus. If I take that cross section and now start to rotate my y-axis real fast, the three-dimensional shape that would be traced out would be this parabolic bowl. Okay, you talk about solids of revolution in calculus. That's what that idea is. But if I think about this, it's telling us it's 8 inches tall. So that right there is 8 inches. From rim to rim, it is 12 inches. So from the axis of symmetry to the rim, so that distance there is 6. So what's that do for me? It gives me this ordered pair right there. If I'm in the coordinate plane, that ordered pair is going to be 6, 8. 6 inches this way, 8 inches that way. This is 0, 0. Okay. Now, the question is, where is the vertex of this, or sorry, where's the focus of this thing? Where's that point at? Well, how do I do this? Well, that point right there is an x, y. We know this thing's opening upward, so it is of the form x squared equals 4py. P is the location of that focus on the y-axis. So what I'm going to do is I'm going to plug in this x and y. X is 6, so I'll go, this will become 36. We got 4 times p times y, which is 8. So I get 32p here is equal to 36. I'll divide both sides by 32. I get 36 over 32 is equal to p. Both those have a 4 in common, so I get into what 9/8 is equal to p. So p here, that distance from the vertex to the focus, is 9/8 inches, or 1 1/8 inch. So that's where I would have to put the filament of the light bulb so that I can harness this reflective property. Hopefully this helps. I'll post a web assignment that goes with this video. And again, if you've got any questions over that stuff, please do not hesitate to ask me.